What are some crazy theories scientists used to believe? Story 1. The idea that mercury was once used as medicine is one of those things that feels almost unbelievable now, especially when you realize just how widespread and trusted it was, despite how toxic it actually is. Because this wasn't some fringe belief or isolated practice. Mercury, in different forms, was used across multiple cultures and time periods as a legitimate treatment, whether as a disinfectant, a laxative, a diuretic, or even as a supposed cure for diseases like syphilis, which at the time was such a serious and poorly understood condition that people were willing to try almost anything that showed even a hint of effectiveness. And in a strange way, it kind of made sense to them. Mercury produces very noticeable effects in the body, things like salivation, sweating, purging, all of which were often interpreted as the body expelling illness, which fit with the medical theories of the time, even though what was actually happening was poisoning. So, doctors would administer compounds like calomel or mercuric chloride, believing they were helping, while in reality, they were introducing something that could be just as harmful, if not more so, than the disease itself. And that's where it gets especially unsettling. Because in some cases, the side effects of mercury poisoning, neurological damage, organ failure, severe physical deterioration, were so extreme that they could be mistaken for the progression of the disease being treated, which made it even harder to recognize that the treatment itself was part of the problem. And then you take it even further back, where mercury was sometimes associated with longevity or even immortality, particularly in certain alchemical traditions, where its unusual properties gave it this almost mystical reputation, leading people to ingest it in hopes of achieving something far beyond simple healing, which, in hindsight, is kind of tragic, because it shows how limited understanding, combined with desperate need and a bit of observational misinterpretation, can lead to practices that feel completely backward from a modern perspective. And that's what makes it fascinating. Not just that they were wrong, but that they were working with the best framework they had at the time, trying to make sense of what they were seeing, even if that framework led them to conclusions that seem almost shocking now. Because it's a reminder that what feels obvious today wasn't always obvious before, and it makes you wonder which of our current assumptions might look just as strange in the future. Story 2. Phrenology is one of those ideas that feels almost absurd now, but at the time it was taken seriously enough that people used it to judge personality, intelligence, and even criminal tendencies just by examining the shape of someone's skull. Because the basic idea was that different parts of the brain controlled different traits, things like aggression, morality, creativity, and that if a particular area was more developed, it would physically push outward on the skull, creating bumps that could be measured and interpreted. And in a very loose sense, it started from something that isn't entirely wrong. Different regions of the brain do have different functions. But phrenology took that idea and stretched it way beyond what the evidence supported, turning it into a system where you could supposedly read someone like a map just by feeling their head. And people believed it. There were practitioners who would examine skulls, produce detailed personality profiles, and even make judgments about someone's character or future behavior based on what they found, which meant it wasn't just a curiosity, it actually influenced how people were perceived and treated. And that's where it gets uncomfortable, because it was often used to justify existing biases, reinforcing ideas about superiority, inferiority, and even criminality in ways that had real social consequences, all under the appearance of being scientific, which is what makes it fascinating in hindsight, because it shows how something can look structured, logical, and evidence-based on the surface, while actually being built on flawed assumptions and selective interpretation. And the people who believed in it weren't necessarily irrational. They were trying to apply scientific thinking with the tools and knowledge they had, but without the methods we now rely on to test and validate those ideas properly. And that's the part that sticks. Because it's not just about a strange belief from the past, it's about how easily patterns can be seen where they don't really exist, especially when they line up with what people already expect to find. And it makes you wonder how many ideas feel just as convincing today, but might not hold up the same way in the future. Story 3. The idea that radiation was once considered good for you is one of those things that sounds completely backwards today. But at the time, it actually felt like cutting-edge science being applied in exciting new ways. Because when radioactivity was first discovered, in the late 19th and early 20th centuries, it wasn't immediately seen as dangerous. In the way we understand it now, it was seen as powerful, almost magical, something that could affect matter and energy in ways people had never seen before. And instead of caution, there was enthusiasm. Radiation started showing up in consumer products, from glowing paints to cosmetics, and even things like health tonics and radioactive water that people would drink, believing it could boost energy, improve vitality, or even extend life. And in a strange way, it kind of made sense to them. Radiation was associated with energy, transformation, something active and dynamic. So the assumption was that small doses might stimulate the body or have beneficial effects, especially since the harmful effects of long-term exposure weren't immediately obvious. But over time, reality caught up. People who were exposed regularly started developing serious health issues, radiation sickness, cancers, severe tissue damage, and suddenly that idea of radiation as something beneficial began to collapse under the weight of actual evidence. And there are cases, like individuals who consumed radioactive products regularly, where the consequences were severe enough to become cautionary examples of just how wrong that assumption had been. And that's what makes it so fascinating, because it shows how something newly discovered, something not fully understood, can be interpreted in completely the wrong way, simply because its effects aren't immediately clear. And the people involved weren't being reckless in the way it might seem now. They were working with incomplete information, trying to apply a new discovery before fully understanding its risks. And that's the part that sticks, because it's a reminder that early interpretations of new science can be wildly off, especially when the long-term effects aren't visible right away. Which makes you wonder what current technologies or discoveries might still have consequences we don't fully see yet, just waiting to be understood later. Story 4. The idea that people would suffocate if they traveled faster than 30 miles per hour is one of those beliefs that sounds almost ridiculous now, but actually makes a strange kind of sense when you put yourself in the mindset of the time. Because before railways, humans had never experienced sustained high speeds. The fastest most people ever moved was on horseback or in carriages, and even that felt intense. So the idea of traveling at speeds far beyond that wasn't just unfamiliar, it was completely outside normal human experience. And when early scientists and thinkers tried to imagine what that might be like, they had to rely on the physics and biology they understood at the time, which wasn't as developed as it is now. So they started asking questions like, what happens to the body at high speeds? What happens to breathing if air is rushing past you? Would your lungs even be able to function properly? And without real-world data to contradict those concerns, it was easy to come to conclusions that now seem completely off. Because from their perspective, it wasn't obvious that the body would adapt just fine, that air pressure inside a moving vehicle wouldn't suddenly strip oxygen away, or that the human body could handle much higher speeds without any issue. So, when trains were first proposed, there was genuine concern that traveling that fast could be dangerous in ways people didn't fully understand. And that's what makes it fascinating, because it shows how limited experience can shape scientific assumptions. Even when people are trying to think logically and cautiously, they weren't being irrational. They were extrapolating from what they knew, just without the benefit of actually testing it yet. And once trains were built and people started traveling at those speeds regularly, it became obvious that those fears didn't hold up, and the whole idea quickly faded. But it's a great example of how even reasonable-sounding concerns can turn out to be completely wrong once reality catches up with theory. And it kind of makes you wonder what current limits we assume exist today. That might turn out to be just as unfounded once we push past them. Story 5. The phlogiston theory is one of those ideas that feels almost bizarre now, but at the time it was actually a serious attempt to explain something people observed every day, which makes it even more interesting when you realize how convincing it once seemed. Because before modern chemistry, people were trying to figure out what fire actually was, not just how it behaved, and the idea they came up with was that burning materials contained this invisible substance called phlogiston, which was released into the air during combustion. So, if something burned well, it was thought to be rich in phlogiston, and when it burned, that substance escaped, leaving behind what they called a dephlogisticated material. And in a strange way, it kind of worked as an explanation for a while. It gave people a framework, something consistent they could apply to different materials, something that seemed to explain why things burned and changed. But then you run into problems. Like the fact that when some metals burned, they actually gained mass instead of losing it, which doesn't make sense if they're supposedly losing phlogiston. So the theory had to start bending to accommodate those contradictions, which is usually a sign something deeper is off. And eventually, with the discovery of oxygen and the development of modern chemistry, it became clear that combustion wasn't about releasing a mysterious substance. It was about reacting with something in the air. But what makes it fascinating is how long the phlogiston idea lasted, and how many smart people worked within that framework before it was replaced. And then you've got the idea of cold as a substance, which feels equally strange now, but followed a similar line of thinking. Instead of understanding temperature as energy, people imagined cold as something that could be absorbed or transferred, like a kind of invisible fluid. So, when water froze, it wasn't losing heat in the way we describe it today. It was gaining cold, which turned it into ice. And again, it sounds wrong now, but it was an attempt to make sense of observable changes using the concepts available at the time. And that's what ties both of these together. They weren't random guesses. They were structured attempts to explain the world before the underlying mechanisms were fully understood, which is what makes them so interesting. Because they show how science evolves, not by jumping straight to the correct answer, but by building models that work just well enough until something better comes along. And it's a reminder that even ideas that feel completely wrong in hindsight were once the best explanations people had, which makes you wonder, which of our current theories might end up looking just as strange one day? Story 6. Lobotomy is one of those things that feels especially disturbing, not just because of what it was, but because of how widely it was accepted for a period of time as a legitimate medical treatment. Because the idea behind it was that by severing connections in the brain's frontal lobes, you could reduce severe mental illness, things like depression, anxiety, schizophrenia, conditions that, at the time, had very few effective treatments and often left patients institutionalized for life. And in the early stages, it actually seemed promising to some doctors. Patients who were previously extremely distressed or agitated could become calmer, more manageable, less overwhelmed by their symptoms, which, in that context, was seen as a kind of improvement. But the reality was much more complicated and much darker. Because while some symptoms were reduced, what was often lost in the process was the person's personality, emotional depth, decision-making ability, sometimes even basic functioning, leaving many patients permanently changed in ways that couldn't be reversed. And what makes it especially unsettling is how quickly and widely it spread. Procedures were simplified, sometimes performed in ways that seemed shockingly crude by today's standards, and thousands of people underwent lobotomies before the long-term consequences were fully understood or acknowledged. And the doctors involved weren't necessarily acting with bad intentions. They were trying to solve a real problem, working in a time where mental health treatment options were extremely limited, and for a while, this seemed like a breakthrough, which is what makes it so fascinating and uncomfortable at the same time, because it shows how something can be introduced as a solution, supported by early results, and then only later recognized as deeply flawed once the full impact becomes clear. And that's the part that sticks, because it's not just about the procedure itself. It's about how easily something can be accepted as progress before its consequences are fully understood. And it makes you wonder how many other ideas in medicine or science might seem effective in the short term, but could look very different with the benefit of hindsight. Story 7. The idea that cigarettes were once marketed as good for you is one of those things that feels almost surreal now, especially when you look at how confidently and widely that message was promoted, because this wasn't some vague belief or underground claim. For a long time, cigarettes were actively advertised as beneficial, even endorsed by doctors in certain campaigns, with suggestions that they could help with stress, aid digestion, soothe the throat, or even improve focus, which in hindsight feels completely backwards given what we now know. And part of the reason it seemed believable at the time was because the long-term effects of smoking weren't immediately obvious. People didn't drop dead after a cigarette. The damage was slow, cumulative, and building up over years, which made it much harder to connect cause and effect in a clear way, especially before large-scale epidemiological studies became common. So instead, people focused on the short-term effects, the calming sensation, the routine, the social aspect, the temporary feeling of relief or stimulation, all of which could easily be interpreted as positive, especially when reinforced by advertising and authority figures. And the tobacco industry leaned into that heavily, using imagery, slogans, and even medical language to create the impression that smoking was not just safe, but actually beneficial, which shaped public perception in a way that lasted for decades. But as research improved and long-term studies began to show clear links between smoking and diseases like lung cancer, heart disease, and respiratory illness, that narrative started to collapse. And what's left now is this stark contrast. Something that was once normalized, encouraged, even recommended in some contexts, now recognized as a major health risk. And that's what makes it so fascinating, because it shows how powerful perception can be, especially when combined with incomplete data and strong messaging. And it's a reminder that just because something is widely accepted, or even promoted by experts at a given time, doesn't necessarily mean the full picture is understood yet, which makes you wonder what current habits or products might still be viewed as harmless, until we know more. Story 8. The idea of massive prehistoric land bridges connecting continents is one of those theories that sounds almost fantastical now, but at the time it was actually a serious attempt to explain something that didn't seem to make sense any other way, because scientists were noticing clear patterns. Fossils of similar plants and animals appearing on continents that are now separated by vast oceans, geological similarities across distant landmasses, connections that were too consistent to just be coincidence. But without the concept of plate tectonics being widely accepted yet, there was a big problem. Continents were assumed to be fixed in place. So, if they couldn't move, how did those similarities exist? And that's where the land bridge idea came in. The assumption was that there must have been enormous stretches of land connecting continents in the past, allowing animals and plants to migrate across. And then somehow, those land bridges disappeared, sinking beneath the ocean and leaving the continents isolated as we see them today. And in a way, it was a logical solution given the constraints. It explained the distribution of life, it fit the observations, and it didn't require rethinking the fundamental assumption that continents were static. But the scale of it was the strange part. We're talking about hypothetical landmasses spanning thousands of miles across deep ocean basins, appearing and disappearing in ways that didn't have strong physical evidence, which meant the theory had to stretch further and further to accommodate new data. And then plate tectonics comes along. The idea that continents actually move, that they were once joined together and then gradually drifted apart over millions of years, carrying life with them. And suddenly, everything clicks. Those fossil connections, geological similarities, all of it makes sense without needing to invent vast, vanishing land bridges. And that's what makes it fascinating. Because the earlier theory wasn't random or careless, it was an attempt to explain real evidence using the best framework available at the time. It just turned out that the underlying assumption that continents couldn't move was wrong. And once that assumption changed, the entire explanation shifted with it, which is what makes it such a great example of how science evolves. Not by ignoring evidence, but by reinterpreting it when a better model comes along. And it also highlights something important. Sometimes the strangest ideas in science aren't the result of bad thinking. They're the result of trying to make sense of real observations without yet having the key piece that ties everything together. And once that piece appears, what once seemed necessary suddenly looks almost unbelievable in hindsight. Story 9. The idea of massive prehistoric land bridges connecting continents is one of those theories that sounds almost fantastical now, but at the time, it was actually a serious attempt to explain something that didn't seem to make sense any other way. Because scientists were noticing clear patterns, fossils of similar plants and animals appearing on continents that are now separated by vast oceans, geological similarities across distant landmasses, connections that were too consistent to just be coincidence. But without the concept of plate tectonics being widely accepted yet, there was a big problem. Continents were assumed to be fixed in place. So, if they couldn't move, how did those similarities exist? And that's where the land bridge idea came in. The assumption was that there must have been enormous stretches of land connecting continents in the past, allowing animals and plants to migrate across, and then somehow those land bridges disappeared, sinking beneath the ocean and leaving the continents isolated as we see them today. And in a way, it was a logical solution given the constraints. It explained the distribution of life, it fit the observations, and it didn't require rethinking the fundamental assumption that continents were static. But the scale of it was the strange part. We're talking about hypothetical landmasses spanning thousands of miles across deep ocean basins, appearing and disappearing in ways that didn't have strong physical evidence, which meant the theory had to stretch further and further to accommodate new data. And then plate tectonics comes along. The idea that continents actually move, that they were once joined together and then gradually drifted apart over millions of years, carrying life with them. And suddenly, everything clicks. Those fossil connections, geological similarities, all of it makes sense without needing to invent vast, vanishing land bridges. And that's what makes it fascinating. Because the earlier theory wasn't random or careless, it was an attempt to explain real evidence using the best framework available at the time. It just turned out that the underlying assumption that continents couldn't move was wrong. And once that assumption changed, the entire explanation shifted with it, which is what makes it such a great example of how science evolves. Not by ignoring evidence, but by reinterpreting it when a better model comes along. And it also highlights something important. Sometimes the strangest ideas in science aren't the result of bad thinking. They're the result of trying to make sense of real observations without yet having the key piece that ties everything together. And once that piece appears, what once seemed necessary suddenly looks almost unbelievable in hindsight. Story 10. The idea that doctors didn't need to wash their hands because a gentleman's hands are always clean is one of those beliefs that feels especially disturbing in hindsight because the consequences of it were so real and so devastating, even though at the time it was widely accepted. Before germ theory was understood, people didn't know that invisible microorganisms could spread disease. So, illness was often explained through things like imbalances in the body or vague environmental factors, not something that could be physically transferred from one patient to another on a doctor's hands or instruments. And in that context, cleanliness was more about appearance than biology. If your hands looked clean, if you were a professional, if you carried yourself properly, then there wasn't really a reason to suspect you might be spreading anything harmful. So, doctors would move from patient to patient, sometimes even from autopsies to childbirth, without washing their hands, not out of negligence, but because they genuinely didn't know there was a risk. And the results were tragic. Mortality rates, especially in places like maternity wards, were extremely high, with infections spreading in ways no one fully understood at the time, which made it even harder to identify the cause. And what makes it even more unsettling is that when figures like Ignaz Semmelweis started suggesting that handwashing could dramatically reduce deaths, the idea was initially resisted, even rejected, because it challenged established beliefs and implied that doctors themselves might be responsible for harming their patients, which was a difficult thing for the medical community to accept. But once germ theory developed and the importance of hygiene became clear, everything changed. And something as simple as washing hands became one of the most important practices in medicine. And that's what makes it so powerful as an example, because it shows how a small misunderstanding, something that seems almost obvious now, can have enormous consequences when the underlying science isn't fully understood. And it's a reminder that sometimes the biggest breakthroughs aren't about complex technology or new discoveries. They're about recognizing something that was right in front of us the whole time. Something simple that just hadn't been understood yet. Story 11. The idea of the planet Vulcan is one of those examples that's actually kind of beautiful in a weird way because it shows science working exactly how it's supposed to, even though the conclusion turned out to be wrong, because at the time, the problem was very real. Mercury's orbit didn't quite match what classical Newtonian mechanics predicted, specifically the precession of its orbit, which was off by just enough to be noticeable, but not enough to be easily dismissed as error. And that's where things got interesting, because astronomers had already seen this kind of problem before and solved it successfully. Uranus wasn't moving quite the way it should have, so instead of abandoning the theory, they assumed something unseen was influencing it, did the math, and predicted the existence and location of Neptune. And when they looked, it was right there, almost exactly where it was supposed to be, which is honestly one of the most impressive moments in scientific history. So when Mercury showed a similar discrepancy, the logic was completely reasonable. Maybe there's another planet, something closer to the Sun than Mercury, affecting its orbit just enough to explain the difference. And Vulcan was born as a hypothesis, not out of wild speculation, but out of a method that had already proven to work incredibly well. And like you said, it wasn't easy to disprove either. Looking that close to the Sun is extremely difficult, especially with the observational tools of the time. So, the fact that Vulcan wasn't immediately found didn't necessarily mean it wasn't there. It could have just been hidden in the glare, passing unnoticed. And that's what makes it such a great example, because for a while, it actually made sense. It fit the data, it followed a successful pattern, and it didn't require throwing out the existing framework. But then Einstein comes along with general relativity, and suddenly the discrepancy in Mercury's orbit isn't caused by an unseen planet at all. It's caused by the curvature of space-time itself near the Sun. And just like that, Vulcan disappears. Not because it was directly disproven in a dramatic way, but because a deeper, more accurate model made it unnecessary. And that's the part that really sticks, because Vulcan wasn't a foolish idea, it was the right idea given the information and tools available at the time. It just turned out that the universe was operating on a level that hadn't been fully understood yet. And that's what makes it fascinating, because it shows how even very precise observations and logical reasoning can still lead you slightly off course if there's a deeper layer you haven't uncovered yet, which is kind of humbling, because it suggests that even now, with everything we know, there might still be Vulcans in our current theories, things that make sense, until something deeper comes along and changes the entire picture. Story 12. The fact that Isaac Newton, one of the most influential scientists of all time, was deeply invested in alchemy is one of those details that really reshapes how you think about the history of science and the people behind it. Because when we think of Newton, we picture gravity, calculus, optics, these incredibly rigorous, foundational contributions that helped define modern science, something precise, logical, almost purely rational. But at the same time, he was spending a huge portion of his life studying alchemy, writing extensively about it, experimenting, trying to understand the transformation of substances, the idea that base metals could be turned into something more valuable like gold, and even exploring more mystical aspects tied to those ideas. And what makes it interesting is that alchemy, at the time, wasn't seen as completely separate from science in the way we think of it now. It was more like an early, mixed form of chemistry, philosophy, and a bit of mysticism, all blended together, where people were genuinely trying to understand the nature of matter and transformation, just without the modern framework we have today. So, Newton wasn't necessarily being irrational. He was working within the intellectual landscape of his time, where the boundaries between what we now call science and what we now dismiss as pseudoscience weren't clearly defined yet. And in a strange way, that makes sense, because the same curiosity that drove him to discover the laws of motion and gravity could also lead him to explore ideas that didn't end up being correct, simply because the tools and knowledge to separate those ideas hadn't fully developed yet. And that's what makes it so fascinating, because it reminds you that even the greatest scientific minds weren't operating with perfect clarity. They were navigating a world where some paths led to breakthroughs, and others didn't. And sometimes, both were being explored at the same time by the same person, which kind of humanizes the whole process, because it shows that progress in science isn't just a straight line of correct ideas replacing wrong ones. It's a messy, overlapping exploration where even brilliant thinkers can invest deeply in concepts that don't hold up later, and that's the part that sticks, because it makes you wonder how many ideas that seem serious and worth pursuing today might eventually end up in that same category, not because they were foolish, but because they were part of the process of figuring things out. Story 13. The ancient Greek idea of the four elements is one of those beliefs that feels almost too elegant, like it should be right just based on how intuitively it explains what people were seeing in the world around them. Because the framework is so simple, everything is made of earth, water, air, and fire, and each of those elements has a natural place in the universe, almost like a built-in order that everything is trying to return to. So when you drop a rock and it falls, it's not just gravity in their view. It's the rock moving back toward its natural home, toward the element of earth. When water flows or rain falls, it's finding its place just above earth. When bubbles rise in water, that's air trying to return upward to where it belongs. And fire, being the lightest and highest element, always moves upward, which makes flames stretch toward the sky and sparks drift higher, as if they're trying to rejoin the heavens, where fire is thought to exist in its purest form. And honestly, it's kind of convincing when you think about it from that perspective, because everything behaves in ways that seem to match the theory, at least on the surface, and without modern physics or chemistry, it provides a really clean, almost poetic explanation for motion, structure, and the natural world. Even the idea that stars are made of fire fits into that system in a way that feels consistent with what people could observe at the time. And that's what makes it such a great example. Because it wasn't random or illogical, it was a structured attempt to explain patterns using the best observations available, and it worked well enough to feel complete. But, of course, as science progressed, we learned that matter isn't made of those four elements, and motion isn't driven by things trying to return to their natural place, but by forces like gravity and interactions at the atomic level. And yet, even knowing that, there's still something satisfying about the original idea, because it shows how humans naturally try to impose order and meaning on what they see, building systems that feel right even if they're not ultimately correct. And that's the part that sticks, because it reminds you that a theory can feel intuitive, consistent, even beautiful, and still be wrong, which makes you wonder how many ideas we hold today feel just as natural, but might eventually be replaced by something deeper that changes how everything fits together. Story 14, the idea of the inheritance of acquired characteristics, most famously associated with Jean-Baptiste Lamarck, is one of those theories that feels so intuitive that it almost seems like it should be correct, especially before you learn how evolution actually works, because the logic is very straightforward. If an organism changes during its lifetime in response to its environment, it seems reasonable to assume those changes would somehow be passed on to its offspring, almost like experience itself is being inherited. So, in the classic example, a giraffe stretching its neck to reach higher leaves would gradually lengthen it over time, and then its offspring would inherit that slightly longer neck, continuing the process generation after generation. And when you look at it casually, it kind of makes sense. It fits with the idea that effort leads to improvement, and that those improvements would carry forward, which aligns with how we tend to think about learning and adaptation on a personal level. But the problem is that biology doesn't work that way. Changes that happen during an individual's lifetime, like muscle growth, injury, or learned behavior, don't directly alter the genetic information passed on to offspring, which means those acquired traits aren't inherited in the way Lamarck proposed. Instead, evolution works through variation that already exists at the genetic level, with natural selection favoring traits that improve survival and reproduction over many generations. But what makes Lamarck's idea so fascinating isn't just that it was wrong. It was one of the first serious attempts to explain how species change over time. It moved away from the idea that life was fixed and unchanging, and toward the idea that organisms could adapt and evolve, which was a huge conceptual step forward even if the mechanism he proposed wasn't correct. And in a way, it highlights how science often progresses, not by jumping straight to the right answer, but by building on ideas that are partially correct, partially flawed, and gradually refining them as more evidence becomes available. And the interesting part is that even today, there are some nuanced discussions around things like epigenetics, where environmental factors can influence how genes are expressed across generations, which isn't the same as Lamarckism, but shows that the relationship between environment and inheritance is more complex than a simple yes or no. And that's what makes it stick, because it's one of those theories that feels logical, almost obvious, until you look closely enough to see where it breaks. And that tension between intuition and reality is exactly what makes it such a compelling piece of scientific history. Story 15. The idea of a concave Earth universe is one of those theories that sounds almost like satire today. But at the time, it was presented with enough mathematical detail and confidence that it actually managed to gain a degree of attention and credibility, because the core concept flips the normal model completely. Instead of Earth being a sphere in space, the idea was that the Earth itself formed the inner surface of a Wishal sphere, and everything else in the universe, stars, planets, light, existed inside that shell, meaning we were essentially living on the inside of a hollow world, looking inward rather than outward. And from that starting point, the theory tried to reinterpret everything. Optics, gravity, perspective, all reworked to fit this inverted geometry, with equations and explanations built to make observations appear consistent with the model, which is part of what made it compelling to some people at the time, because it wasn't just a vague idea, it was dressed up in scientific language and reasoning. And then you get to the part that makes it almost surreal. The claim that, based on this model, long-distance artillery could be used in a completely different way, with the suggestion that instead of firing toward a distant target along the surface, you could fire upward into the interior of the universe and have the trajectory curve around to hit a location like France, which, when you say it now, sounds completely detached from reality. But it was taken seriously enough that there were actual attempts to test related ideas. Though as you'd expect, nothing came of it in any meaningful or successful way. And that's what makes it such a fascinating example, because it shows how a theory can appear structured and convincing if it's built carefully enough, even if the foundational assumption is completely wrong. The math, the explanations, the confidence, all of it can give the impression of legitimacy, at least until real-world testing or deeper understanding exposes the flaws. And the people involved weren't necessarily trying to be absurd. They were exploring a model that, within its own internal logic, seemed to explain certain things, even if it required ignoring or reinterpreting a lot of established evidence. And that's the part that sticks, because it highlights how important the starting assumptions are in science. If those are off, even slightly, you can build an entire framework that looks coherent, but leads you somewhere completely disconnected from reality. And it's a reminder that just because something can be described with equations and technical language doesn't mean it reflects how the universe actually works. Story 16. The idea of the luminiferous ether is one of those theories that feels incredibly logical when you first hear it, to the point where it almost seems strange that it isn't true. Because in the 19th century, scientists understood waves in a very specific way. Sound waves needed air, water waves needed water, vibrations needed some kind of material to travel through. So when light was understood to behave like a wave, the natural assumption was that it must also require a medium, and that medium was called the ether, an invisible, all-pervading substance that filled the entire universe, even what we think of as empty space, acting as the stuff that light waves move through, something present everywhere but impossible to detect directly. And it made perfect sense at the time, because without it, you'd have waves moving through nothing, which didn't fit with how physics was understood. So, the ether became a foundational concept, something scientists built theories around, something they expected to eventually measure or interact with in some way. But then experiments started to challenge it. Most famously, attempts to detect Earth's motion through this supposed ether kept coming up empty, producing results that didn't match what the theory predicted, which created this growing tension between expectation and observation. And eventually, with the development of Einstein's theory of relativity, the need for the ether just disappeared. Light didn't require a medium in the way people had assumed, and space itself didn't need to be filled with some hidden substance to support it. And that's what makes it so fascinating, because the ether wasn't a wild or irrational idea. It was a direct extension of how people understood waves and physics at the time, a perfectly reasonable attempt to fill in a gap in knowledge. It just turned out that the assumption underlying it, that all waves require a medium, didn't apply in this case. And once that realization happened, the entire concept became unnecessary almost overnight. And that's the part that sticks, because it shows how even very intuitive ideas, ones that feel almost obvious based on prior knowledge, can end up being completely wrong when applied in a new context. And it makes you wonder how many concepts we currently take for granted, simply because they fit what we already know, but might not survive once we understand things a little more deeply. Story 17. The early ideas about human anatomy, especially around reproduction, are one of those areas where you can really see how a lack of direct observation, combined with cultural beliefs, led to explanations that feel almost surreal today. Because for a long time, detailed anatomical study was limited, restricted, or even discouraged, which meant that a lot of what people believed about the body wasn't based on direct evidence, but on interpretation, symbolism, and secondhand ideas passed down over generations. So when it came to female anatomy, the uterus in particular ended up surrounded by all kinds of misconceptions, including the belief that it was horned or shaped in ways that reflected symbolic or mythological ideas rather than actual biology, which shows how easily observation could be mixed with imagination when there wasn't a reliable way to verify things. And then you have beliefs about semen that are just as fascinating. The idea that it originated from the brain, or was closely tied to vital essence, meant that ejaculation was seen as more than just a physical act. It was thought to involve a loss of something fundamental, something tied to mental clarity, strength, or even spiritual energy. So, the act itself wasn't just biological, it was interpreted as a kind of depletion. And again, when you step back, you can see how they got there. Without an understanding of cells, reproduction at the microscopic level, or the actual function of organs, people tried to connect what they could observe, physical changes, fatigue, patterns, to larger frameworks about health, balance, and the nature of the body. And those frameworks often blended science, philosophy, and cultural beliefs into one system that felt coherent at the time. But, of course, as anatomy advanced, especially through dissection and later scientific methods, those ideas started to fall apart, replaced by a much more accurate understanding of how the body actually works. And that's what makes it so interesting. Because it's not just about being wrong, it's about how those ideas were constructed in the first place. They weren't random. They were attempts to explain something complex with limited tools and incomplete information, shaped by the worldview of the time. And that's the part that sticks, because it shows how easily gaps in knowledge can be filled with assumptions that feel logical, even convincing, until better evidence comes along and changes everything. And it makes you realize what feels obvious now, it was anything but obvious back then. Story 18, the idea that everything in the universe was made up of just 4 elements, earth, water, air, and fire, is one of those beliefs that feels almost poetic in how neatly it explains the world, even though we now know it's fundamentally incorrect. Because from the perspective of ancient thinkers, especially in Greek philosophy, it actually works surprisingly well as a framework. You could look around and categorize almost everything you saw into those 4 types. Solid things like rocks and soil as earth, liquids as water, gases as air, and anything involving heat or transformation as fire. And suddenly the complexity of the world becomes something much more manageable and understandable. And it didn't stop there. Each element was thought to have its own natural place and behavior, which helped explain motion and change, like why objects fall, why flames rise, why water flows, all tied into this larger idea that everything is trying to return to its proper state. So it wasn't just a classification system, it was a full explanation of how the world worked. And that's what made it so powerful, because it gave people a sense of order, a way to connect observations into a coherent system without needing to understand atoms, molecules, or the underlying physics that we rely on today. But as science progressed, especially with the development of chemistry, it became clear that matter is made up of elements in a completely different sense. Atoms with specific properties, far more numerous and complex than just 4 basic categories. And the behaviors those ancient thinkers were trying to explain turned out to be driven by forces and interactions that operate at a much deeper level. And yet, even knowing that, there's still something fascinating about the original idea, because it shows how humans naturally try to simplify complexity into patterns that feel intuitive, building systems that capture part of the truth, even if they miss the deeper structure underneath. And that's the part that sticks, because it's a reminder that a theory can feel elegant, consistent, and even obvious, and still be incomplete. Which makes you wonder how many of our current frameworks, no matter how advanced they seem, might one day look just as simple in hindsight. Story 19. That early misunderstanding around X-rays is one of those stories that, whether every detail is perfectly documented or not, captures something very real about how new technology can be misinterpreted in ways that have serious consequences. Because when X-rays were first introduced, they were revolutionary. For the first time, doctors could actually see inside the human body without cutting it open, which must have felt almost unbelievable at the time, like suddenly having access to something that had always been hidden. But with that kind of leap, there's always a problem. You're seeing something new, without fully understanding how to interpret it. So, when doctors compared images of living patients to earlier anatomical references, they noticed differences, like organs appearing lower or sagging compared to what they expected, and without realizing that those reference images often came from cadavers lying flat, they interpreted that difference as something abnormal, which led to a very human kind of mistake, trying to fix what they thought was wrong. And in that context, surgery seemed like a logical response, even though, as we now understand, the body naturally shifts under gravity depending on position, and what they were seeing wasn't a problem at all, just a difference in perspective. And that's what makes it such a powerful example, because it's not about ignorance in a simple sense. It's about how easy it is to misread new information when you don't yet have the framework to interpret it correctly. The technology was right, the observations were real, but the conclusion, I was off. And the consequences of that gap between observation and understanding could be severe, especially in a field like medicine where acting on incorrect assumptions can directly affect people's lives. And that's the part that sticks, because it shows how even a breakthrough, something that represents huge progress, can still lead to mistakes if it's adopted faster than it's fully understood. And it's a reminder that seeing something clearly isn't always the same as understanding it correctly, especially when you're looking at it for the first time. Story 20, the idea that blowing smoke up someone's butt comes from an actual medical practice, is one of those things that sounds like a joke, until you realize it's rooted in something that really did happen and was taken seriously at the time. Because in the late 1700s, along the River Thames and places like London, there were emergency kits specifically designed to revive drowning victims, and one of the recommended methods involved using bellows to pump tobacco smoke into the rectum. And the reasoning, while strange now, actually followed the medical thinking of the time. Tobacco was believed to have stimulating properties, and introducing smoke into the body was thought to warm the victim internally, stimulate breathing, and essentially jumpstart the system, especially in cases where someone had been pulled from cold water and appeared lifeless. So, these kits weren't hidden away or experimental. They were placed in accessible locations, intended for real emergency use, which shows how accepted the practice was. And like a lot of early medical ideas, it wasn't completely random. It likely drew from earlier practices, including those used by indigenous peoples who had long-standing knowledge of tobacco and its effects, though applied in very different contexts, such as treating certain types of pain. But somewhere along the way, that idea was adapted into something much more extreme, based on an incomplete understanding of physiology and how the body actually responds to trauma like drowning. And eventually, as medical knowledge improved, especially with better understanding of respiration and circulation, the practice was abandoned, replaced by more effective methods like artificial respiration. But what makes it fascinating is how it reflects the mindset of the time. People were trying to intervene, to save lives, using the tools and knowledge they had, even if those methods seem completely misguided now. And the phrase itself stuck around, evolving into something symbolic rather than literal, used to describe flattery or exaggeration rather than an actual procedure. And that's the part that makes it memorable, because it's not just a strange historical footnote. It's a reminder that even serious, widely accepted practices can later look almost unbelievable once we understand things more clearly, which again raises that same question. How many things that seem normal or even helpful today might look just as strange in the future? Story 21, the fact that even into the 1980s, a noticeable number of geologists still didn't accept plate tectonics, is one of those examples that really shows how slow scientific consensus can be, even when the evidence is already pretty overwhelming. Because today, plate tectonics feels completely foundational. It explains earthquakes, volcanoes, mountain formation, the movement of continents, the distribution of fossils, basically the entire large-scale structure of Earth's surface. And it's hard to imagine geology without it, but that wasn't always the case. For a long time, the idea that continents could move was seen as speculative at best, especially when it was first proposed earlier in the 20th century, because there wasn't a clear mechanism explaining how massive land masses could drift across the planet. And in science, that matters. It's not enough for something to look right. It has to work within a framework that makes sense physically. So, even though there was strong evidence, like matching coastlines, fossil distribution, and geological similarities across continents, many scientists remain skeptical because the underlying process wasn't fully understood yet. Then, mid-20th century discoveries start changing things. Seafloor spreading, magnetic striping on the ocean floor, better mapping of tectonic boundaries. Suddenly the mechanism becomes clearer, and the theory shifts from speculation to something much more solid. But even then, acceptance wasn't instant, because science isn't just about data, it's also about people, careers, training, established ideas, the frameworks people have spent decades working within. All of that creates inertia, and changing a foundational belief takes time, even when the evidence is strong. So the fact that some geologists held out into the 1980s isn't really about ignorance. It's about how deeply rooted scientific paradigms can be. And that's what makes it fascinating, because it shows that even correct ideas don't immediately take over just because they're correct. They have to be tested, argued, refined, and gradually accepted, often over decades. And it's a reminder that science is not just a collection of facts. It's a process, a human process, where even something as central as plate tectonics can go from controversial to obvious, but not overnight, which makes you wonder what ideas today, even well-supported ones, might still be in that transition phase right now. Story 22, social Darwinism is one of those ideas that's especially disturbing in hindsight, not just because it was wrong, but because of how confidently it was presented as science, and then used to justify real harm on a massive scale. Because what happened essentially was that concepts from evolutionary theory, particularly ideas associated with Charles Darwin, were taken out of their proper biological context and applied to human societies in a way that distorted both the science and its implications. Instead of describing how species evolve over time through natural selection, social Darwinism reframed it into a kind of social philosophy, where competition between groups of people was seen as natural and even desirable, and where outcomes like wealth, power, or dominance were interpreted as evidence of inherent superiority. And from there, it didn't take much for those ideas to be shaped by existing prejudices. Racial hierarchies, colonial attitudes, and economic inequality were all reinterpreted as natural results of this supposed struggle, which allowed people to present deeply biased and harmful beliefs as if they were objective, scientific truths. And that's where it becomes especially dangerous, because once something is framed as science, it carries authority. It feels justified. It feels harder to question, which meant these ideas were used to support policies and practice that cause real suffering, from discrimination and segregation to forced sterilization and other forms of systemic injustice. And what makes it particularly unsettling is that it wasn't just fringe thinkers pushing this. There were academics, institutions, and policymakers who embraced these ideas, reinforcing them in ways that made them seem legitimate for a long time. But over time, as both science and society progressed, it became clear that these conclusions were not only ethically wrong, but scientifically flawed, based on misunderstandings of evolution and misuse of data. And that's what makes social Darwinism such an important example, because it shows how easily scientific concepts can be misapplied when they're taken out of context and combined with existing biases. And it's a reminder that science isn't just about discovering facts. It's about interpreting them correctly, carefully, and responsibly. Because when that process breaks down, the consequences don't stay theoretical. They affect real people in very real ways. And that's why this one stands out, not just as a mistaken idea from the past, but as a cautionary example of how powerful and dangerous bad interpretations of science can be. Story 23. We used to believe that electrons and atoms orbit around the nucleus in neat little circles, kind of like tiny planets spinning around the sun. And honestly, it made perfect sense at the time because early models of the atom were heavily inspired by what we could actually see in space. So, scientists basically shrunk down the solar system and said, yeah, it probably works like that too. Which is why you'll still see those classic textbook diagrams with electrons going around in clean loops, like some kind of atomic racetrack. But here's where it gets weird. because that idea is actually completely wrong, or at least wildly oversimplified. And the more scientists started digging into quantum mechanics, the more it became clear that electrons don't follow fixed paths at all, and instead exist in these fuzzy regions of probability called orbitals, which basically means we can't pinpoint exactly where an electron is, only where it's most likely to be at any given time. So, instead of imagining a tiny marble circling a nucleus, you should picture something more like a cloud that changes shape depending on energy levels, sometimes looking like blobs, dumbbells, or even more bizarre shapes that feel straight out of abstract art. And the electron is somehow everywhere in that cloud until you try to measure it, which is where things get even more mind-bending. And yeah, it turns out the universe at that scale doesn't really care about our need for clean, predictable orbits. And the truth is way messier, way harder to visualize, and honestly, way cooler. Story 24. When the atomic bomb was first tested, there was this genuinely terrifying concern floating around among some of the scientists that the explosion might literally ignite the atmosphere and burn all the oxygen in the world, which sounds like something straight out of a sci-fi apocalypse, but was actually taken seriously enough to be discussed before the Trinity test in 1945. The idea came from the fact that nuclear reactions release insane amounts of energy and heat, way beyond anything humanity had ever created before. So there was this lingering fear that it could trigger a runaway reaction in the air itself, specifically by fusing nitrogen atoms or setting off a chain reaction involving oxygen, basically turning the entire sky into fuel. What's wild is that physicists like Edward Teller actually explored this possibility in calculations, because even though it sounded extreme, nobody had ever detonated something like this before, so there wasn't exactly a rule book to follow, and the stakes were obviously as high as they could possibly get. In the end, more detailed math and theoretical work, including contributions from Hans Bethe, showed that the conditions needed to ignite the atmosphere just weren't achievable with nuclear weapons, since the energy would dissipate too quickly and the reactions wouldn't sustain themselves. So, when the bomb finally went off in the New Mexico desert, the world didn't end in a global firestorm, but the fact that some of the smartest people alive even had to ask that question in the first place really shows how unknown and unsettling that moment in history actually was. Story 25, I'm probably late to the party, but yeah, organic chemists genuinely used to wash their hands with benzene like it was just another lab convenience, which is kind of insane when you look at it from a modern perspective, because today it's one of those chemicals that comes with very serious hazard warnings and strict exposure limits for a reason. Back in the early to mid-20th century, though, lab safety standards were, let's just say, a bit more casual, and benzene was everywhere because it's an incredibly effective solvent, especially for dissolving organic compounds, greases, and residues that soap and water just wouldn't touch. So, if your hands were covered in some stubborn reaction byproduct, benzene was basically the go-to quick fix. The problem, which we now very clearly understand, is that benzene isn't just kind of bad, it's strongly linked to diseases like leukemia, and prolonged exposure can seriously mess with bone marrow and blood cell production, meaning people who worked with it regularly, especially without gloves or ventilation, were putting themselves at real risk without fully realizing it at the time. And the wild part is that this wasn't some obscure fringe practice either. It was common enough that older chemists will casually mention it like, yeah, we used benzene to clean everything, which feels almost surreal now given how tightly controlled it is in modern labs. It's one of those reminders that science didn't just evolve in knowledge, but also in how seriously we take safety, because a lot of what we consider obvious today was learned the hard way. Story 26, 9 out of 10 doctors choose Camel cigarettes, is one of those ads that sounds so absurd today that it almost feels fake, but it was actually a real marketing campaign run by R.J. Reynolds Tobacco Company back in the mid-1900s. And it worked way better than you'd expect, because at the time, cigarettes weren't widely accepted as dangerous in the way we understand now. The whole idea was simple, but insanely effective. If doctors, the people you trust with your health, are supposedly choosing a specific cigarette brand, then it must be safe, or at least less harmful, right? And companies leaned hard into that perception by running surveys, often with questionable methods, and then turning the results into bold, confident claims that showed up in magazines, billboards, and basically everywhere. This was all happening before the full risks of smoking were publicly established, long before major reports like the 1964 Surgeon General's Report on Smoking and Health officially linked cigarettes to serious diseases. So there was this weird window of time where tobacco companies could blur the line between medicine and marketing without much pushback. And yeah, looking back, it's kind of surreal that something as harmful as cigarettes was once promoted with the help of medical authority. But it also shows how powerful advertising can be when the science isn't fully settled yet, and how easily trust can be borrowed, packaged, and sold. Story 27. Scientists used to believe that frogs literally just appeared out of mud, and that maggots crawled into existence from rotting meat, which sounds ridiculous now, but was actually part of a long-standing idea called spontaneous generation, where people thought living organisms could just arise from non-living stuff under the right conditions. And to be fair, if you didn't have microscopes or modern biology, it kind of looked that way, because you would see a puddle or swamp sit there for a while, and suddenly it's full of frogs. Or you leave meat out and boom, maggots everywhere, with no obvious parents in sight. So, the conclusion people jumped to was that life was somehow just forming directly from the environment itself. This belief stuck around for centuries and was even supported by some big names, until experiments started poking holes in it, especially the work of Francesco Redi in the 1600s, who showed that if you cover meat so flies can't get to it, no maggots appear, which was a pretty big clue that something else was going on. Later on, Louis Pasteur basically shut the whole idea down with experiments using sterilized broth and specially designed flasks, proving that microorganisms come from other microorganisms, not from thin air or random sludge. So yeah, what looked like life popping into existence was really just life we couldn't see yet doing its thing. And once the tools caught up, that mystery disappeared pretty quickly. Story 28. Honestly, this is one of those humbling reminders that being wrong doesn't mean being stupid. It usually just means you're working with limited information and trying to make sense of what you can actually observe, which is exactly what humans have always done. Take the idea that the sun goes around the Earth, like with the geocentric model, because if you just look up at the sky every day, that's exactly what it seems like is happening. The sun rises, moves across, and sets. And nothing about that screams, by the way, you're actually spinning at insane speeds on a rock orbiting a star. Same with Phlogiston theory, where people thought burning objects released some invisible substance, because when you watch wood or coal burn, something clearly leaves the material, flames, smoke, heat. So the idea that a thing is escaping doesn't feel unreasonable at all. It just turns out the explanation was off. Even the heart being tied to thought and emotion wasn't random. It's where you physically feel reactions like fear, stress, excitement. So linking it to intelligence wasn't some wild leap, just a misinterpretation of real bodily signals. And with spontaneous generation, again, leave meat out and maggots show up, no visible cause, no obvious parents. So the conclusion that life just appears feels like a logical guess without microscopes or germ theory. The pattern here is kind of fascinating because people weren't just making things up for fun. They were building models that matched what they could see, hear, and feel. And a lot of those models actually worked well enough to stick around for centuries until better tools, better experiments, and better frameworks came along and replaced them. So yeah, a lot of crazy ideas aren't really crazy in context. They're just early drafts of understanding, and the only reason they seem obvious now is because we're standing on top of all the corrections that came after. Story 29. That quote gets passed around a lot, usually to show that even brilliant people can be wildly wrong, but it's a bit of a mixed bag in terms of accuracy and context, especially when you're talking about someone like William Thomson, first Baron Kelvin, who was one of the most respected scientists of his time. The tricky part is that there's no solid evidence he actually said all of those things exactly like that, at least not in one neat quote, and some of the lines are probably misattributed or exaggerated over time, which happens a lot with famous figures because it makes for a better story if even a genius got everything wrong. That said, Kelvin did express skepticism about certain emerging technologies, particularly early aviation, which makes more sense when you realize that in the late 1800s, powered flight really did seem unrealistic given the engineering limits of the time, and heavier-than-air machines had repeatedly failed. So, doubting them wasn't some irrational take, it was based on the evidence available then. Same idea with things like radio or X-rays. These were brand new, barely understood phenomena, and early demonstrations could look unreliable or even like tricks. So hesitation wasn't stupidity, it was caution in the face of incomplete data. What's interesting is that Kelvin wasn't some clueless outsider. He contributed massively to physics and engineering and helped shape the very scientific framework that later proved those ideas possible. Which kind of reinforces the bigger point. Progress isn't about always being right, it's about refining ideas over time, even if that means today's certainty becomes tomorrow's outdated take. Story 30. The tongue map is one of those science myths that just refuses to die, even though it's been debunked for decades, and it's a perfect example of how something can look convincing, get printed in textbooks, and then just stick around way longer than it deserves. The idea was that different parts of your tongue are responsible for different tastes, like sweetness at the tip, bitterness at the back, sour on the sides, and so on, which sounds neat and organized, but the reality is way messier and way more interesting because taste receptors for all basic tastes are actually spread across most of the tongue. This whole thing traces back to a misinterpretation of research by David P. Honig in the early 1900s, where he measured slight differences in sensitivity across the tongue, not exclusive zones. But when his data got simplified and translated over time, it somehow turned into this rigid map that made it look like each region only detected one taste. And once that version made it into textbooks and classroom posters, it basically took on a life of its own, because educational materials don't always update quickly, and if something is easy to teach and visualize, it tends to stick, even if it's wrong. Modern science shows that taste is a combination of signals from all over the tongue, plus smell and even texture, meaning flavor is way more of a full sensory experience than a neatly divided chart. So, yeah, the tongue map isn't just wrong. It's kind of a cautionary tale about how oversimplified explanations can outlive the actual science by a long shot. Story 31. It sounds bizarre now, but René Descartes genuinely believed the soul had a physical seat in the brain, and he landed on the pineal gland as that spot, partly because it's a single central structure rather than a paired one like most of the brain, which to him made it a perfect candidate for something unified like the soul. His idea was that this tiny gland somehow acted as the interface between the immaterial mind and the physical body, basically letting the soul influence movement and perception. And while the steering the brain like a rider on a horse analogy is more of a modern way of describing it, it's not that far off from how he imagined the interaction working. What's especially interesting is how this philosophical idea overlaps with real anatomy, because the habenula, which connects regions of the brain and has links near the pineal gland, gets its name from Latin for little rein or strap, like the reins used to guide a horse. Now, that naming isn't because scientists were secretly agreeing with Descartes about the soul literally steering the brain. It's more about how early anatomists used familiar objects to describe structures they were seeing, but the coincidence is still kind of poetic, especially given the whole control metaphor. Of course, modern neuroscience doesn't support Descartes' view at all. The pineal gland is mainly involved in regulating sleep cycles through melatonin, not housing anything like a soul, but it's a great example of how early thinkers tried to bridge philosophy and biology using the limited knowledge they had at the time. Story 32. The whole bee field idea sounds like something straight out of a sci-fi parody of physics, but it actually comes from a real misunderstanding about how bumblebees fly, not from scientists seriously proposing that bees had some kind of secret anti-gravity gland. The myth really traces back to early attempts to apply fixed-wing aerodynamics, the same principles used for airplanes, to insects like the bumblebee. And when you plug a bee's size, weight, and wing area into those equations, it kind of looks like they shouldn't be able to generate enough lift to stay airborne, which led to that famous but misleading claim that, according to physics, bees can't fly. But the problem wasn't the bees, it was the model. Because insects don't fly like airplanes at all. Their wings don't just glide through the air, they flap incredibly fast and create complex, unsteady airflow patterns, including tiny vortices that boost lift in ways early equations didn't account for. Once scientists started studying insect flight more closely, especially with high-speed cameras and better fluid dynamics models, it became clear that bees are actually really good at flying, just using a completely different mechanism than what people initially assumed. So, the whole bee field explanation is more of a joke or exaggerated retelling that popped up later, playing on the idea that if the math doesn't work, maybe the bees are breaking physics somehow, when in reality, physics was never wrong. We just didn't fully understand how it applied in that situation yet. Story 33, it's kind of wild, but Linus Pauling, one of the most respected scientists ever, and one of the very few people to win 2 Nobel Prizes, chemistry and peace, spent a big chunk of his later life convinced that high doses of vitamin C could prevent or even cure serious diseases like cancer, along with everything from the common cold to heart disease. And this wasn't some fringe opinion coming from nowhere. Pauling co-authored papers and books promoting what became known as orthomolecular medicine, arguing that optimal health could be achieved by adjusting the concentrations of substances normally found in the body, with vitamin C being his main focus, often in doses far beyond what most doctors would recommend. The problem is that while vitamin C is absolutely essential, and yes, it does cure scurvy, large-scale clinical studies over time just didn't support the idea that megadoses could treat cancer or dramatically prevent illness in the way Pauling claimed. And the medical consensus today is that its benefits are much more limited. What makes this story interesting isn't just that he was wrong, but that it shows how even top-tier scientists can become deeply attached to an idea, especially later in their careers, and continue to defend it despite growing contradictory evidence. So, yeah, it's less about he didn't understand science and more about how being brilliant doesn't make you immune to bias, especially when you're emotionally or intellectually invested in a theory you really want to be true. Story 34. Wait. No. Remove. Not allowed. We must not invent entity types. Use normal. Miasma theory is one of those ideas that sounds almost laughably simple now. But if you put yourself in that time period, it actually made a lot of sense. The basic idea was that diseases were caused by bad air, like foul smells coming from rotting matter, sewage, or swamps. And honestly, if you've ever smelled something truly awful and felt like it must be unhealthy, you can kind of see where they were coming from. Before microscopes and modern biology, people had no way of seeing bacteria or viruses, so they relied on patterns they could observe. And one of the most obvious patterns was that disease seemed to cluster in places that smelled terrible, overcrowded cities, open sewers, piles of waste. So the conclusion was basically, the smell itself is making people sick. This idea, known as miasma theory, dominated medical thinking for centuries and even influenced how cities were designed, with efforts to improve sanitation, ventilation, and air quality, which ironically did help reduce disease, just not for the reason they thought. It wasn't until scientists like Louis Pasteur and Robert Koch came along and developed the germ theory of disease that we finally understood the real culprits were microorganisms, not smells themselves. So, yeah, miasma theory was wrong, but it wasn't completely useless because the push to clean up cities and improve hygiene ended up saving lives anyway, even if the reasoning behind it missed the mark. Story 35. It honestly does count, because a lot of early science was basically philosophy trying to explain the physical world. And Aristotle was one of the biggest influences on how people thought about motion for nearly 2,000 years. His take was that objects moved according to their natural place and purpose. So, heavy things like rocks and earth wanted to go down toward the center of the world, while lighter elements like fire wanted to rise upward, which sounds kind of poetic, but was actually his way of explaining everyday observations without any math or experiments in the modern sense. And honestly, if you just watch things fall or flames rise, it does kind of look like they're following some built-in tendency, so the idea that objects have a sort of internal desire to move in certain directions didn't feel crazy at the time. It was just the best explanation available without physics as we know it. The arrow thing is even more interesting, because Aristotle couldn't explain how something keeps moving after it leaves your hand, so he proposed that the air itself rushes in behind the arrow and keeps pushing it forward, which, again, sounds wrong now, but it's actually an attempt to solve a real problem: why motion continues after the initial force is gone. It wasn't until much later, with people like Isaac Newton, that we got the concept of inertia, the idea that objects in motion stay in motion unless acted on by an external force, which completely replaced Aristotle's explanations. So, yeah, he was wrong, but he was also asking the right questions. And for a very long time, his answers were the closest thing people had to a working model of how the world behaved. Story 36. Phrenology is one of those ideas that feels obviously wrong now, but at the time it actually looked scientific enough to convince a lot of people, which is part of what makes it so unsettling in hindsight. The core idea behind phrenology was that different mental traits, like intelligence, aggression, or morality, were tied to specific regions of the brain, and that you could basically read a person by feeling the bumps and shape of their skull. It was popularized in the 1800s by figures like Franz Joseph Gall, and it spread like crazy because it gave people a simple, physical way to categorize personality and behavior, which is something humans are naturally drawn to, especially when it comes with charts, measurements, and a kind of scientific aesthetic. The problem, obviously, is that it was completely wrong. The shape of your skull doesn't determine your intelligence or character, and the brain doesn't work in that simplistic, compartmentalized way. But that didn't stop phrenology from being used to justify some really harmful ideas. It got tangled up with racism, sexism, and social hierarchy, where people would claim that certain groups were inherently inferior based on skull measurements, reinforcing existing biases under the guise of science, which made it even more dangerous because it gave prejudice a veneer of legitimacy. So, yeah, phrenology isn't just a funny, outdated theory. It's a reminder that bad science can still have very real consequences, especially when it aligns with what people already want to believe. Story 37, yeah, tobacco smoke enemas are one of those "this can't be real" things that absolutely were, and they were actually used for quite a long time, especially in the 1700s and early 1800s. The idea was that blowing smoke from tobacco plants into the rectum could stimulate the body, warm the organs, and basically kick someone back to life, especially in cases like drowning, where the person appeared lifeless. It sounds completely absurd now, but in the context of the time, it kind of followed the logic of earlier medical theories, particularly ideas related to stimulating the body and restoring balance, and even ties loosely into older frameworks like miasma theory and humoral medicine, where treatments were more about restoring flow or energy rather than targeting specific biological causes. There were even specialized kits for this, sometimes called fumigation devices kept along rivers like the Thames, where rescuers could use bellows to literally pump smoke into a person as part of a resuscitation attempt, which is just wild to imagine now. The reasoning was that tobacco had stimulating properties, which it does thanks to nicotine, so forcing it into the body might revive someone or relieve internal issues like abdominal pain. But, of course, none of this actually worked in the way they hoped. Eventually, as medical science improved and people started understanding respiration, circulation, and the actual effects of nicotine, the practice faded out and became more of a historical curiosity than a serious treatment. It's one of those examples where people were clearly trying to help and work with what they had, but without the underlying biology figured out, the methods ended up being very questionable. Story 38, frontal lobotomies are one of the clearest examples of something that was once considered cutting-edge medicine, but now feels deeply disturbing in hindsight. The procedure, known as a lobotomy, involved severing connections in the brain's frontal lobes, which are crucial for personality, decision-making, and emotional regulation. In the 1930s and 40s, this was seen as a breakthrough for treating severe mental illnesses like depression, schizophrenia, and other forms of what we'd now call psychopathology, especially because there were basically no effective medications at the time. So, doctors were desperate for anything that could calm patients or make them more manageable. The most famous figure behind it was Antonio Egas Moniz, who actually won a Nobel Prize for developing the technique, which shows just how accepted it was in the medical community at the time. Later, doctors like Walter Freeman popularized even more aggressive versions, including the infamous ice pick method, which could be done quickly and without full surgery. And here's the unsettling part. In some cases, patients did appear better, but that was often because they became emotionally blunted, passive, or unable to express distress, not because the underlying condition was actually cured. Over time, as the long-term effects became clear and better treatments like psychiatric medications were developed, lobotomies fell out of favor and are now considered a dark chapter in medical history. It's a pretty stark reminder that effective can sometimes just mean it made the problem quieter, not that it actually solved it. Story 39, yeah, this is pretty much the core of how science actually works, and it's something people often misunderstand when they look back at wrong ideas from the past. Science isn't a collection of beliefs that scientists vote on. It's a process, specifically the scientific method, where hypotheses are tested against evidence, and the conclusions are always provisional, meaning they're only as good as the data available at the time. So, when you see things like miasma theory, phrenology, or spontaneous generation, it's not that scientists were blindly believing nonsense, it's that they were building the best models they could from incomplete data, limited tools, and observations that did point in certain directions, just not the correct ones. Less data naturally means a wider margin for error, and science has always acknowledged that, even if not explicitly in every case. What's important is that science has built-in mechanisms for self-correction, new evidence, better experiments, improved technology, all of which can challenge and replace older ideas. That's how we moved from Aristotle's motion theories to Newtonian physics, and from there to even more refined models later on. And yeah, anything we label today as what scientists used to believe usually falls into two categories. Either it was a reasonable hypothesis given the evidence at the time, or it's something that got outdated as new data came in and the model was revised or discarded. So the real takeaway isn't that science gets things wrong, it's that science is designed to be wrong sometimes and then fix itself, which is exactly why it works so well over the long run. Story 40. Hollow Earth is one of those ideas that sounds like pure fantasy now, but for a while it actually had some semi-serious backing, mostly because people just didn't know what was going on deep beneath the surface of the planet. The concept, known as Hollow Earth, basically claimed that the Earth wasn't solid all the way through, but instead had vast empty spaces inside, sometimes even entire hidden worlds. Back in the 17th century, Edmund Halley, yes, the same guy associated with Halley's Comet, actually proposed that Earth might be made up of multiple concentric shells, partly to explain weird magnetic behavior that scientists couldn't fully account for at the time, which again shows how these ideas often came from trying to solve real problems with limited data. Later versions got way more out there, with claims of entrances at the poles, inner civilizations, and even entire ecosystems inside the planet, which is where it fully drifted from speculative science into straight-up pseudoscience and mythology. The reason it stuck around is pretty simple. For most of human history, we had zero direct access to Earth's interior, so people filled in the blanks with imagination. And it wasn't until advances in geology and seismology that we could actually map the internal structure of the planet. Now, we know Earth has a layered structure: crust, mantle, outer core, inner core, and it's very much not hollow, but the hollow Earth idea is a perfect example of how, when there's a huge gap in knowledge, people will come up with explanations that feel just plausible enough to stick around for a while.